Hello everyone. Thank you for joining our presentation today. My name is Naoki Nishimoto from R&D department of Fujifilm. And maybe you know our product, Fujinon lens. And I'm responsible for product development of machine vision lenses. Before we start, I'd like to tell you why we chose today's contents. We are aware that designer and installer of machine vision system are tired with their work because there are a lot of requirements with different applications, many applications, and also a lot of lenses and cameras in the market. Then we think that it is possible to make it easier if we could choose a good lens. So we will cover these 2 points today. First is challenges in lens design and cause for image defects. And here we will see 3 different image defects and the reason. And second point, the Fujifilm definition of a good lens. And here we'd like to propose our new classification for machine vision lenses as a good lens. So, first of all, lens is a device to copy an environment on a sensor. But it's not possible to copy 100% because aberration occur due to the physical reason. So lens manufacturer always fighting with minimizing these aberrations. Then let's go into see image defects. First one is one-sided blurring. And first of all, I'd like to explain this image. This is resolution map in color. And then red shows high resolution and blue shows low resolution. Then in this case, resolution is asymmetry and has very beautiful round shape. And then lens is assembled perfectly. And also lens and cameras are set perfectly. Then image plane of lens and sensor of camera fit together perfectly. So we can get like this resolution feature. But the actual situation is like this. Image plane and sensors are tilted. And then only focus on one side, and the other side is defocused. Then the resolution becomes like this. Only one side we can get high resolution, but on the other side, low resolution. So we cannot detect anything. So first image defect is one-sided blurring. Cause is image plane or sensor are tilted. Second image defect is peripheral blurring. This is because image plane is curved. A bit strange, but actual situation. Image plane is curved. What we call field curvature aberration. If lens has big field curvature aberration, we can only get resolution on center, and the corner we lose resolution. defocused. Or if we focus on periphery, and then we lose center resolution. Therefore, if we had field curvature aberration, either center or periphery can be focused. And here, there is some notes. Field curvature aberration becomes bigger and bigger when we use wider angle lens. And the angle getting wider and wider, then this aberration getting bigger and bigger. And also, macro shooting. If we, the object distance getting shorter and shorter, then also field curvature getting bigger and bigger. Then there is one solution. It is using floating lens. Maybe you've heard of floating lens, but let's see what it is. There is at this time same picture, but the left side is standard lens and right side is floating lens. And then what difference between them is focusing mechanism. When object moves, we need to make focusing, and standard lens, it moves lens groups together, same direction, same distance. On the other hand, floating lens, it moves lens groups separately, different way. And then what is good for floating lens? And then first, when we design standard lens, we set one object distance and one F number, and other parameters as well. We set one condition. And then this condition is the best performance we can get. On the other hand, once the condition, for example, distance is changed, then we lose the performance with the standard lens. Then floating lens. Since we can design lens groups position according to the different object position and F numbers and so on, we can design according to the condition. So, for example, one smooth object, then standard lens, field curvature occur because only one condition, now it's different from best position. But floating lens, it was designed according to each conditions. So we can keep image very good state. This is why floating lens is one of the solutions for field curvature. But floating lens is not perfect. We need to take care about flange back length. Flange back length is the distance between flange surface of mount to the image plane. And then once this distance has not high accuracy, then floating lens lose their performance. So if we use floating lens, then we need to use camera which has very accurate flange back length. This is the point to use floating lens. Then third image defect is blurring at a small aperture. I assume that many people think resolution is improved if we close iris and more, then we can get higher resolution. Let's see it's true or not. And then before that, I need to explain one important thing, depth of focus. Depth of focus is the width which we can see image clear if image plane is within the depth of focus. And depth of focus is defined by permissible circle of confusion and F number. Then this depth of focus is defined. And maybe it's new word for you, permissible circle of confusion. It is like sensor pixel pitch. And sometimes we take it 1 pixel, and sometimes 2 pixels, 3 pixels. It depends on the object size, how small or big it is. Then this circle diameter will be changed. Okay, then now this image was simulated by some our lens, and now F number 2, then this image has field curvature and corners are out of the depth of focus. So periphery resolution is a bit lower than center. Then what will be with f5.6? Yes, it becomes dark, but field curvature image is in the depth of focus now. So resolution is improved. So yeah, so far this is correct. When we close iris, then resolution is improved. Then how about f16? Then depth of focus becomes much longer, but we lose resolution. This is what we call blurring at a small aperture caused by diffraction. Then let's see what is diffraction. There is, it shows two different ways to bend light. First one is refraction. Light comes from here and passes through a lens, then it's bent, let's say, and after that, condensing. The other way is diffraction. Once the light contact solid, then light is bent and also spreaded like this. And then it causes blurring. Please take here, for example, sensor. Then the spreaded image makes blurring. Then we think about lens, and first refraction, and after that, at this time, this solid we can think as iris blade. Then it's spreaded by diffraction. So we have blur image. But in this case, iris is full open, and then the area of clear image is much bigger than blurring area. So total image, we can see it's clear image. But once we close iris very much, like this. First, image becomes very dark. And diffraction, actually the area of diffraction is not changed, same as open state. This area is same, but the area of clear image is now very small, and then total image becomes very blurry. This is the cause of blurring at a small aperture by diffraction. Yeah, this is diffraction. So when we set lens to the system, please take care not to close iris so much. This is the point. Then we covered 3 different image defects. And from now, let's go to the Fujifilm definition of good lens. Maybe it's very simple. No one-sided blurring. And second is no peripheral blurring. And third is no 1 and 2 with bright F number. Then how to do that? First is high precision assembly technology is needed. And second is floating design technology. It's a bit complicated, our optical designer, especially for small pixel bits. And the third point, we need total ability. It's a design and accurate parts and high precision assembly. And important one is thorough quality control. Then we achieved those 3, and then now we'd like to propose a new classification of machine vision lenses as a good lens. This is 4D high resolution. And what is 4D? 2D is image area, vertical and horizontal. And another D is working distance. And last D is F number. So keeping high resolution under these 4 factors, then it makes, it can, keep high resolution. Even if we change working distance and F numbers, we can keep high resolution up to corner of image. Then high performance for all applications. We don't think about which lens is good for this application, this application. With 4D, we don't have to think about it. So if you are interested in 4D HR lenses, then please visit our booth. Thank you very much.